about the how it came about that I proposed this harmonics theory. And so now I have done a lot of tests of it. I mean, this is the whole thing. It's no good having a theory if you don't test it. So I've done some cases where I've made predictions without knowing about what data existed, or even if it did exist. And then I've published that material, and then I've sorted out and found that it did confirm what I predicted. And in some other cases, I would call them explanations rather than predictions, where may have been things I already knew, or just where we can see the same structure that I predicted existing in those things. Before going through that, I'll just bring up a couple of my ones from yesterday to okay. Oh, it's up. Yeah, maybe. Yeah, I don't know if you can see that. They're right. This is the spectrum that's predicted by the harmonics theory for the universe, and this scale is the scale of the universe. And I've got 10 to the 18 through to 10 to the 36 through to 10 to the 54. This part you should ignore because the calculations have been incomplete. I've identified that at the scale, at the 10 to the 13th harmonic here is actually the Hubble scale. So all of that is larger than the Hubble scale, and then this coming on down. And there is this envelope there, which is basically a lot like noise. You could call it 1/f noise or something, this stuff in the background, but there are these certain number of frequencies that stand out, are much stronger than the other ones, and give some structure to the universe. So what I'm talking about very much is the structure of the universe. I'm trying to find how I make this do things. Where's that mouse? Is there a mouse? You do it with this. Okay, I got it.
Does anybody know how to dim the lights?
No, you just had it there and I turned that one off.
Oh, I see, okay. So we turn this one off.
Yeah, and that is done.
Oh, okay.
Oh, I've got to hit escape on that one first. Is it escape that gets out of that one?
Sorry, hold on, let me help you. What do you want? Do you want to?
I want to pick a different one.
Try the arrow, please.
Oh, I'll just go down with those, okay. I've probably done something funny. I've hit escape.
On the maps, not easy. Put that into
How do I scroll this? Oh, with the bar.
You should just, yeah, just scroll past it.
Oh, okay.
And then try it to working. There you go.
Okay, thanks. Yeah. I'm just learning how to use the computer, sorry. I'm having trouble finding one. I've accidentally.
Hold on. Let's put the.
Actually, if we're on that
scroll
one,
through.
well, if I go from there, we'll go to the next one. I'm not getting that.
Yeah, because I'm going to bring the mouse over to the other screen.
Yeah.
Click here.
Oh, it's on screen, really? Right.
Yes,
I
this is
see.
on the screen. And then you want to blend.
Actually, that one's okay. Just that one there would be a good one.
Oh, you want to click on here?
If I'm on that one and I can go to the next one, that's fine.
Oh, okay. You want to do that? Okay. Go to the next one.
And there's actually,
There it is.
that's
The right arrow.
This here graph is the envelope of the other one. So it's showing you what are the predicted strongest cycles that will exist under the structure. And along the top, I'm not sure if you can see these, but starting from the fundamental cycle of the universe pulsation, these are the ratios going to the subsequent harmonics. And so the second strong harmonic is 2. And so there's a ratio of 2 from 1 to 2. And then the next strongest one is 4, so it's got a ratio of 2 going to that. And the next strongest one is 12, it's got a ratio of 3. So this has got these ratios 2, 2, 3, 2, 2, 3, 2, 5, 2, 3, and so on. And these are the ratios going from one to the next harmonic all the way down. And that's the predicted structure of the very strongest cycles. Now I should mention that when you have a cycle of standing waves in space, it's doing two things. You've got an oscillation like this. When you make a harmonic of it, you get the second harmonic like this. The 2 is dividing space in half and is doubling the frequency. That one goes twice as fast as this one. when you divide it by 3 or 12 or some other thing, it divides the space by that number, 12 say, and it multiplies the frequency by that. So both space and time are divided up in exactly the same way under the theory. So that's an important point that we will, and I will show you a number of cases where it can be identified that there are known cycles in something, and there is known structures in space that correspond to that. And we will have that from the supergalactic scale down through the scale of stars and to the scale of planets, and show that those things exist on both. And this structure shows that there are these regular peaks that are happening at ratios of about 10 to the power of 4.5 between the things like the Hubble scale, the scale of galaxies, the scale of stars, the scale of planets, the scale of moons, a couple of missing ones, and then the scale of cells, atoms, and nuclear particles. So that's the axiom I'm working from. The universe consists of a standing wave which develops harmonically related waves, and each of these does the same, and that's the result, that calculation. I'd shown you earlier Dewey's table that showed a lot of cycles related by ratios of 2 and 3, starting from a number at 17. He had 17.75 years. And what I've done here is I've just shown this ratio of 2 this way and 3 this way. And this is the table that more or less that Dewey had. But what I've shown is there are a set of other ones that are 5 times that much, which we get these 5s and occasionally other larger primes occurring in that sequence. And we see that there are a lot of common cycles here, like 11 and 22 years are common. And people have talked about a 20-year, 60-year and 180-year cycles in the climate. And you'll see here 19.77, 5.93, 177.9 years. These are ones that do pop up in the climate. Also 355 years was identified by Chizevsky in the climate. And then we get to some longer scales which are in the tens of thousands of years, up to tens of thousands of years, and on up. And these are like mass extinction cycles and geological cycles. And we come down to one which would be some solar cycles, some shorter solar cycles. This one, I did that one yesterday, didn't I? There were a number of reports, but I did this one yesterday which was about a number of cycles found in the sun. And this is all done after Dewey and after my original work. I found that there were these guys who had mentioned a set of cycles found in the sun that they had observed. The astronomers themselves had written that these were harmonically related cycles. And one is the rotation of the sun, not as seen by the Earth, but as in sidereal, 25.8 days, and they had identified 52 days, 103 days, 77 days, 155, and 464 days, all related by ratios of 2 and 3, and all observed in a number of different things. Some of these cycles are observed in the rate at which neutrinos come out from the sun. Some of them are observed in sunspots, some are observed in gamma rays, and all sorts of different things that are happening on the sun. And that these linked into a couple of the known cycles in the economy. So we see that this ratios of 2 is actually linking together external to the Earth and internal to the Earth cycles. Now this is one area where I had made an earlier prediction that of the different scales at which we would expect larger than galaxy clusters to form. And this, I came across this one. It was published in New Scientist in 1990, and they call it Galaxies Form Megawalls Across Space. So this is showing us in megaparsecs out to 1500 with the megaparsecs are based on an assumed Hubble constant of 100 kilometers per second, which now actually measured to be about 71. And this is showing how many galaxies were found at that distance. Now, there was a joint American-Australian project where they looked in 2 opposite directions, and they just sampled out a very long way. They called it a pencil beam, and this is the distribution they got. And you can see there's a very, very clear periodic structure of these peaks. There are a lot more galaxies, and so they're calling them megawalls. You can see there's also some secondary ones. There's some secondary ones going on there. There's some shorter period things happening as well. Now, this particular one is very interesting because now when they said that these are intervals of 128 megaparsecs, what they really mean based on the Hubble constant of 100 kilometres per second per megaparsec. What they really mean is they found them at 12,800 kilometres per second intervals when you interpret the redshift as a speed, right? So this is now, the numbers they quote are 2 steps removed from what they've really measured. They've really measured a bunch of redshifts at equal intervals of redshift, right? And but when you do this, based on the latest Hubble constant, and I went into Wikipedia and got the 10 latest determinations of the Hubble constant and averaged them out, and they came to 71.2 kilometres per second per 71.2 kilometres per second per megaparsec, which, as Martin said, is really an inverse time, and which they say 13.7 billion years now. That figure I was able to predict successfully about 20 years ago, once I knew from a Russian man, who I mentioned before, Professor Afanasiev. He had this cycle of 586.24 million years in geology. When you use the latest value of the Hubble constant average from those 10, and the value I predicted a long time ago based on this, that gives 586 million light years that these apart. So we've got 586 million light year spacings, distances, and a period of 586 million years in the geological deposits measured. So what that shows is these are light speed phenomenon. There are waves there that are oscillating in 586 million years and have got this 586 million year wavelength.
Excuse me, just to get this right in my mind, is each peak 500 million light years apart?
Yes, this is the space between these big peaks.
Thank you.
Yes. Yeah. There are some smaller ones in between. I didn't manage to get the data for that, so I read it all off the graph, and I put it in the computer as I did an analysis of it. And when I did that analysis, can you see those fine lines there, the spectrum? So you can see here that there are a bunch of peaks, and just about all the peaks except a couple here are exact multiples of that one in terms of the frequency. So you can see that there is this harmonic thing, in particular that 4, 5, and 8 and 10 are the stronger ones there that are present. So there is a lot of finer detail there, continuing down to the 2, the 4, and the 8 are the other additional ones that are mentioned by the geologists as being additional cycles. So the shorter term geological cycles are also present in here as well, showing that all that wave structure is existing there. In 1994, I came across some stuff that said that there was a 72 kilometres per second quantum in galaxy distances, or in galaxy velocities they call it, but they're in distances, in red shifts. And I thought, okay, at that stage, that was before I did this other one, I thought, okay, I divide that I divide the speed of light by a strong harmonic, which is 2880, and I got 104 kilometres per second. I thought, that's funny, why is it 72? And about a year went by, well, that must have been 93, because I did this in 94. About a year went by when I just couldn't reconcile that. And then I suddenly realised Einstein had this velocity addition formula, and it doesn't matter how many times you add 72 kilometres per second, you never get to the speed of light. So I said, what happens if you add it 2,880 times? And the answer is you get to 0.693 of the speed of light. And I thought, okay, what redshift is that? And it comes out the redshift is exactly 1. In other words, if you have galaxies at a distance where the redshift is 1, that means all the frequencies we see from them are exactly half the ones that we have on Earth. So in harmonics theory, this ratio of 2 is very important, and so this is the first place at which you get feedback. It's hitting a different harmonic now. The feedback is to the second harmonic. Then when you divide that by 2880, it gives you 72.153 kilometres per second. And it turns out that around that time, Tift had put down a paper where he measured it as 72.135. And he said it's plus or minus about 0.01. So that agreed extremely well with that. And at that stage, I made this prediction of a whole bunch of other ones. So like there's 144, 72, 36, these are kilometres per second, 24, 18, 12, 9, 6, 4, 3. And I put some asterisks beside the ones that were the very strong ones. And one of these ones over here is the one that they're getting with the galactic clusters. And so I put this list in the Usenet groups, and one very kind guy Donald Wells, I think his name was, he said to me, you might want to look at this TIFF paper published in Astrophysics Journal, and so I went and had a look, and TIFF said he had found 72 kilometres per second, 36. He mentions basically the list that in the range that he'd done, which was this range, he had every one that I predicted except one, and he had one more. And the one more he had was 2.67. This is the same data, but just in a graphic form. Was 2.67, which was just below the threshold at which I'd stopped doing the ones that I put on the list. So there was exceptionally good agreement between what he had found and what I had predicted. And in fact, if you do a statistical test on it, it's something like 1 chance in 10 to the 30 that we get such good agreement between two sets of data over that interval. So this was one of the really best tests that that the whole thing was working. We'll be down the other end of the talk that when I get to the other really best test of the prediction. This one here shows the I've mentioned, I think already, that no, I'll get to that next. This here shows the velocity of the planets and their motions around the Sun. Mercury has a velocity of 48 kilometres per second, Venus 35, Earth 30, Mars 24, Ceres 18, and then the other planets a little bit more random, but these ones, the little V's I put here, are equal intervals of 6 kilometres per second multiples, and some of them are on the 12 as well. So these, the planets, apart from Venus, which missed by 1 kilometre per second, all of the others are exactly on the multiples of 6 kilometres per second. So what we're seeing is this redshift business that's going on that shows these steps is reflected. The galaxy motions, or apparent motions, in redshift are reflected in the motions of the inner planets, not so much the outer planets. We'll see the outer planets come on a different basis. So and I've found also that the nearby stars tend to have these sort of velocities going to each other as well. Just a little peak. There are a whole wide spectrum of ones with stars, but there's more concentrations at those points. When we look at the speed of sound in different materials, that has there are peaks also in velocities where there's more, and I do an analysis method which I call Kotov's method, which I'll explain in a moment, and that shows up the structure, and it shows that there are several particular speeds of sound that things like to be fractions or multiples of, and it fits in with the same structure. So velocities, it's not surprising if we have distance structures done harmonically and time periods done harmonically, it's not surprising that velocity, which is distance over time, shouldn't also show the same harmonic structure, and we find that that's the case. And now these numbers may be too small to see. Can anyone read those? No. Okay, I'll just describe what it is. This guy Kotov, a Russian astronomer, he particularly noticed that there's a lot of stuff going on associated with a period of 160 minutes. So, for example, the Sun actually has an oscillation in a period of 160 minutes. I noticed in one of Reg's graphs that had a daily chart that it had 9 wobbles in each day. 160 minutes is exactly the 9th of a day. At one stage they thought it was the oscillation of the Sun was actually an effect of the Earth, because it was so accurately 1/9 a day. But eventually they measured that it was 160.010, so it was actually slightly different. The method that he uses is, if he's got a set of values, and in this case I've used the distances of the planets from the Sun. I had 9 planets because there were 9 then, and I believe they're going to put Pluto back in, so this will come right again. What you do is you take a value. In this case I've taken 0.349 astronomical units, and then you see how it divides into each of these here, and you get the divisor, and you see how near to integers they are. We're trying to find something that commutes with them all, and the planets tend to be at multiples of 0.349 astronomical units. In this case, Mars and Saturn don't fit, but the rest of them are all fairly near, and you add up how much they missed. What is the fraction that they missed by? So what I do is I'm varying here from 0.1 astronomical units through to a couple of hundred something, And for each test value, I'm working out how well does it commute with the set of values I've got. It's either dividing it into it or dividing it by the value and finding out how much it misses from an integer and adding all those up. And then because we're used to spectrums sticking upwards when it's important, I've inverted the final answer. And this shows you the spectrum on this commutation thing of Kotov's of the planets. The distances that they like to be multiples or fractions of, which is presumably some sort of waves in space that have got these particular distance scales. And we see there's two very strong ones here at 5 and 10 astronomical units. That's because the outer planets, if you take Saturn, Uranus, Neptune, Pluto, they're very close to 10, 20, 30, 40 astronomical units from the Sun. And Jupiter is half of that at 5. So you can also do it with 5, in which case it works also for Jupiter. But these values are also, the inner planets tend to be fractions of those as well. So when we take 5 astronomical units, as well as the outer planets being 1, 2, 4, 6, 8 times that, the inner planets, apart from Mars, the Earth is 1/5 of that, Venus is a 7th, and Mercury is 1/13. So we get 8 of the 9 planets fit into that. When we go to 10, we get a similar sort of story. So these ones, these are the peaks, which these two here are the inner planets. The inner planets tend to be multiples of this, and it also fits in that one. And that's about 0.35 astronomical units. There's actually 2 peaks there, and we find that we find that this whole typical spectrum of the harmonic structure, that we've got a ratio of 2 to this one. This is a ratio of 7 from there to, but there's some more at 2, 2, 3 happening there, and another 3 here. And this is the very typical pattern of the harmonic series with a lot of 2s, a couple of 3s, and the other odd prime now and then. This 7, I'll get you to remember that. There's a ratio of 7 or 14 between the scale of the inner planets and the scale of the outer planets. I mentioned there's a 160-minute oscillation of the Sun. There's also the things called the 5-minute oscillations. Now there's a whole bunch of those. They actually range from about 3 minutes to about 11 minutes, with the peak at about 5.5 minutes. And so you'll notice that these peaks are much sharper and these ones are a bit more ragged, and that's because there's many waves coming from the Sun in that range, and so the poor planets don't know which one to fit. And so the inner planets are a bit rough in terms of their distance scales of being multiples 1, 2, 3, 4, whereas the outer planets are very smooth on that. But when we look at the velocities, the inner planets are a very good fit to multiples of a certain velocity, whereas the outer planets aren't. So it's the velocity that's working the inner planets, and it's the distances that are working the other ones. There's one more that comes out here, which is a distance of 515 astronomical units. So it's way out of the solar system, but this one in fact has the strongest fit of all to the thing. It fits for all the planets except Mercury. So I'm predicting that at some stage they will discover a lot of stuff at close to 515 astronomical units from the Sun. So there's a new prediction for you. It hasn't yet been
515 astronomical units.
515, yeah. Okay, so that's the solar system. A lot of people have done Bode and Titus, and a lot of other people have looked at this structure of the solar system distances, and a lot of people looked at galaxies, but no one had done stars. I couldn't find any reference to people doing stars. So at that stage I had Norton Star Atlas. This sounds a bit primitive, but I got the nearby stars in Norton Star Atlas, and I put them in the computer, and in 3D I calculated the distance between every pair of all the close stars. So I didn't just want to do from us, I did every pair. And I put them in a little histogram, and this was as I posted it years ago in Usenet, graphics using text, right?
What do you mean by every pair?
Every pair. So if there's 100 stars, you've got 100 times 99 divided by 2 pairs, right? Because, so we've got us to Alpha Centauri, us to Sirius, but we've also got Alpha Centauri to Sirius.
Okay, right? Each star relative to every other star.
Every, yeah. Okay. And so this is going from naught to about 13 astronomical units. And we'll see this, there's a binary star Alpha Centauri, which is at naught. There's one at 2 years, one at 3 years, and there's a big cluster around about 4.5 light years. There's another peak at 6, another one at just over 7, and a big cluster at just under 9, a huge heap at 9.6, and a huge peak at 11.86 light years. Now, you might remember some of those figures. These were the figures that I originally found in my economic cycles, and then that one as well. And this is the one that was one very popular cycle, 9.6 years, in the Canadian lynx and a number of other animal populations. So these distances in light years are matching, the peaks in that are matching the time periods of common cycles on Earth in years. So when the astrologers say the stars are influencing the Earth, they're right, but they got the method wrong. The method is, it's the distances of them and the standing waves that they're on that are affecting the cycles on Earth. So this is the second match, well, it's the third actually, because I mentioned the agreement between the solar cycles and the distances of the planets. I mentioned the geological cycles, the distance of the galactic clusters, and this is cycles on Earth and the distances. So all those three confirm that the waves that are doing this are in existence still, and that they are light speed waves, because years and light years, the ratio, the velocity has to be the speed of light to do that. Now, I was particularly interested in this 4.45 and the 8.9 because that was the strongest one. I took these stars in 3D and I varied a parameter continuously in number of light years, and I varied the direction it looked in space continuously all over the sphere, so that takes a few combinations, and I looked for what is the best thing if there's a grid of stars, and it turned out that the best thing is 4.43 light years comes out as a grid space. That compared to Dewey's 4.44 year cycle and my 4.45 year cycle, so they're all very tightly clustered. And it turned out that there were 5 directions in which the stars tended to form a grid. One of them is more or less the galactic plane. It's got teensy tilt because the stars are actually doing that as they go around the galaxy, so there's a slight up and down. There were 3 axes that were nearly orthogonal, and another which had seemed to be the local stars, and another 2 that looked like they might be more galactic things. They aren't exactly orthogonal. If you were to have 4 stars arranged in a square, then that would be 4.44 light years, say, but the diagonals would be the square root of 2 times that. And the square root of 2 doesn't feature in the harmonics at all. We don't get another harmonic of that. However, if you give those a teensy twist, then it turns out that when that axis is 3 over 2, that one is extremely close to 4 over 3. And those ratios occur in the harmonics all the time. And so the distances, so that's how it's able to do these other distance quanta at the same time, because one of those these other ones will have relationships of 3 to 4 and 2 to 3 and so on. So there is this structure in space. So the positions of the stars are nothing like random. I described this to some famous astronomer in Princeton, and he said, no, that's not possible because they're all moving. And I said, well, they're like that now, and you can't imagine how it can stay like that, but no one could imagine the 5-sided symmetry that was found by the English guy, and that turned out to be true. I said, there may be forces that are acting on the stars. These larger waves may be pulling them back into position, slight accelerations that are not ones that we know about, and that sort of thing could explain stuff in galaxies. Do I press the space bar or something? Yeah. And so I made a prediction that it seems probable that if this position is to be maintained, that there would be accelerations of stars. Now the data exists to do this, but I've never managed to get it. There's some people that have measured the recession or velocity of stars extremely accurately in order to discover planets. And they discovered hundreds of planets before anyone else started to discover them. And that data, I believe, should have superimposed on it very slight accelerations, and that those accelerations should be wherever a bond like Alpha Centauri is at 4.31 light years from us, not 4.44, which is the grid unit. And therefore it's slightly closer. Therefore that's if we think of like bonds in a crystal, when sound and that travels through it, they're doing this all the time. So this one's been compressed a bit, so there should be an acceleration away from us for that one, although we have to sum the acceleration over many stars to get what they would be. But it's possible to do that calculation and to test if there really exist these accelerations. If that's true, then we can say that there is a lot of mass in these very large-scale waves that's not being assumed by the astronomers, and this can explain a lot of the missing mass. I did a calculation way back. I'm not 100% convinced about it, but it did give a missing mass formula that fitted to reasonably well to
The star, so was this is this the star data that's mapping to here? Is this a data that's mapping to there? Or is this your extrapolation?
No, this here is purely the actual positions of stars. It's just
The
a
actual
histogram of the
positions.
actual distances between stars.
And so the data that you got, is it for the close stars measured with
Yeah, this is
parallax, or
just
is
the
it
close stars, yeah.
with a parallax?
Yes, by parallax, yes. So
Oh.
you can't go very far by parallax. Since then, they've vastly improved the accuracy, and so the numbers could be done again on a much
The reason
larger
I'm
data.
saying is
I
because
haven't done that.
anything beyond parallax, I
Yeah.
find is highly,
Yeah.
you know, okay.
Questionable.
Questionable.
I seem to have lost what to do here. I've lost the ability to move.
Oh yes, that's because you hit the space bar.
Yeah.
Just touch it. Just
I'll touch
the
this one.
thing,
Yeah, okay.
Or just move your nose. Okay,
Thank you.
you've got the ability back.
Thank you. I've mentioned this whole structure of cycles that are found. They've got these ratios of 2 and 3 in this whole structure. It's often found by getting cycles from many different things and seeing them. But in this case, there's one thing which shows a huge range of cycles which show the structure all in the one thing. This is a measure of solar magnesium-2 index. It runs from 1978 to 2006, so 28 years of monthly data, and this is the spectrum. So what it's showing is there's a huge peak at 26.74 days, which will be the solar rotation period. Right? There's a bunch of other peaks that are half that, particularly strong ones are half and a quarter, and that's because the current sheet around the sun does this sort of thing as it goes around, so you get divisions by half and a quarter. Sometimes it has a different arrangement, and you do get a third, a fifth, and a sixth showing up in there. So these can all be understood in terms of the solar structure. And so there's no surprise that we've got 1, 2, 3, 4, 5, 6 harmonics. Harmonics theory would expect that you get the 2 and the 4 to be the stronger ones. Now what I've taken is this little bit of the thing here and I've expanded it out, and it's showing that there is additional peaks at 51.6 days, 114 days, 158 days, 321, and 642 days. Now I put them above them in blue. That's 2 times the original. This one's a bit rough. It's near 4 times. You can see that there's a broad peak there, and the peak is the top of the middle of the broad peak is at the correct place, but there's one particular period that's a little bit off. And this one is at 6 times, 12 times, and 24 times the solar rotation period. So these things are all present in this magnesium-2 solar flux index, and it's showing from 6 times 24, 140 over a ratio of 144, and showing exactly the sort of structure harmonics theory predicts. Now, I think these can be explained by standard things. I don't believe you can explain subharmonics. Indian rainfall, I actually use the square root of the rainfall because it has such wide ranges and the peaks are so big compared to the rest, and it makes the oscillations a bit more less skewed when I use the square root of the rainfall. And then I remove the seasonal effect because they have the monsoon, so you get this huge rainfall at one time and then it's dry for months. Changes little difference. So I use that. So I do that adjustment on the data just to make it usable by removing that. And when I do that, this is the spectrum. It shows a set of periods: 75 days, 153 days, 300 days, and 600 days. These 4 green things are exact ratios of 2 apart, and you can see they very closely match those same periods that were found in the sun are appearing on the Earth in the monsoon rainfall. And there are a couple other periods as well, but most of the peaks there are explained by that single one series of W frequency. These are some rocks that are found north of Auckland, where I live, and that's just a tiny piece of it. It looks like someone's laid paving stones right up this beach. Very wide beach, very long, and there's all these uniform ones, and when you go along you think, gosh, a lot of those are very accurate, the same size. And I was measuring this with my shoe, and a lot of them were 1.1 times the length of the shoe, and some other ones were 2/3 of that, and so on, and did all this. And then I measured my shoe when I got home, and yeah, that's about 30 point something, a little over 30 centimetres, and I'm doing all this, and then I went, hang on, just over 30 centimetres, that's a foot. these were a foot long, and some of them are, and there were there were a number of other different structures, and it turned out there were things, there was a yard, there was a fathom, a yard, a foot, a cubit, and a span, which are all ratios 2 and 3. They're the old imperial system units, here they are in nature. Now I call this one rock music because there's, you can see, I've put the red marks there are at equal intervals, and you can see we've got a period 2, period 2, period 2, period 3, period 3. So I put them with quavers and dotted quavers, and we've got some, you know, and we get, and sometimes get one where there's a couple of the shorter ones, you know. So, and someone, when I told someone about that, they said, yes, Pythagoras said, are not rocks frozen music? That's right, they are. Just to show you how this happens in human affairs as well, we're not separate from this phenomenon, we're part of it. This one's a little bit more complicated what I've done. I took the IBM share price over a daily share price over quite a long period, and can't see where that period is, possibly my paper. And then what I did is I analysed it using standard software to get find out what cycles were present. I took the 67 strongest cycles that were found, that were all significant, and I put them into a further analysis because sometimes you get a little cluster of cycles together, and I wasn't so much interested in the cluster as the sort of central trend of them. And I used that method of Kotov's analysis again to look for communalities in amongst those. So it's looking for periods. So what this is a graph of is periods that tend to strongly be related by integer ratios to all those 67 cycles that are found in IBM share price. And what do we find? We find a peak at 2.5 days, a peak at 5 days, a peak at 10 days, 20 days, 60 days, and 120 days. They're the strongest ones. Ratio 2, ratio 2, ratio 2, ratio 3, ratio 2. A very typical harmonic structure. These periods at 120 days is also 0.33 years, and I didn't go far enough with Dewey's table, but the two, he has one very strong cycle of 0.99 years, and at 0.33 and 0.66 years, that's 0.33 years, that's probably 0.66 years, I mean. They are also common cycles, and these other ones fit off that. The guy, Hurst, who did a lot of analysis of markets, used these cycle periods, but they're heavily modulated, so you can't just fix it through the whole period, you have to keep track of it along the way. But this shows very clearly that share prices are very strongly affected by cycles around those periods that move around a little bit as they go.
You should be a millionaire by now.
Yeah. Well, who says I'm not? I did run a unit trust for a little while, okay? Now this one is copper prices. And this is from 1784 to 1993. And it's a graph of, on a log scale of copper prices. Now, what I've done is I've put some coloured dots here. And the cycles I've put, you will notice that the peaks are very sharp. You haven't got this sort of thing going on, you've got toom, toom, toom. And this is a thing that's described by Hurst, and he said that in these things, the cycles align with their peaks together. So we line them as if there's cosines, right? And so a long, slow cycle, the peak of that will have the faster cycle, and the still faster ones will all line up. So you get very sharp peaks on them. And the cycles I've done are 178 years, 89 years, 59 years, 35.6 years, which is my old friend the ratio, 29.7, which is half of 59, 17.8 and 11.86 years. They were all very common cycles that are well known, and I put the coloured dots with them, so you can see a huge set of dots on that one and that one, because the whole lot come together there. That's 178 years apart, and you can see that's the biggest peak in that part, and that's the biggest peak in that part. So that's quite clearly where the 178-year cycle comes to a peak. And then I put every one of the peaks of every one of those in there. I haven't missed some out because they didn't fit a peak. There's no peak at that one because there was missing data in that period. So there probably was one, but we haven't got a record of it. And you can see that, that the ones that have got particularly multiple ones have generally got quite a big peak. But sometimes where there's just one, there's also a big peak. It may be that this one has got 17.8 years. That one is I haven't done here the harmonics of 8.9 years, 4.5 years, which were a couple that I found. So those ones will have come together there, which are shorter harmonics. But you can see that all of these peaks are being driven by a whole series of harmonically related cycles. There's vast numbers of them you have to add up to get to this, but you can see it really is happening, it really is working. The structure is there, present in that. You too can be a millionaire. But I'm not taking any money from you for this, so if it doesn't work out, don't blame me. I got the nearby galaxy distances. I think I got these from Wikipedia, all the nearby galaxies, and again I applied Kotov's method to it and looked at their distances from us. I'm not sure if I did all the two-dimensional ones in this or not. I might have done. And then I get rid of that. I analysed those to see, are there some particular distances that galaxies like to be apart? And you can see there's two peaks there. I had identified a 2.22 million light year one as fitting in this whole structure, and there's one very close to that. They probably wouldn't claim that the figures are more accurate than that, but there's one also at 2.58. That's because that's the distance to Andromeda, and there's a whole cluster of hanger-on ones with that go with that. There's also one at 414,000 light years and one at 167,800. This is about the distance of the Magellanic Clouds from our galaxy, and about the same for the two hanger-ons to Andromeda. When I was explaining about this one time, one guy, I said to him, it's a bit like, I was talking about chemical bonds and that in relation to some of these things, and he said, yes, he said, I've often thought Andromeda and us are H2O molecules. And you're right, there's two little ones, the H's, and this big one, the O. That's the galaxy, right? So galaxies form molecules as well, right? And H2O is a popular one, assuming we are O. I mean, there might be some other one with two O's, with two H's. But that's, so this one here, I had identified as probably 1/12 of that one, but I think it's actually coming out slightly more on here. But that's, we take the distances with a tiny grain of salt because they're possibly not that accurate, but we can see that, oh, that one is worth mentioning, the 414,000 light years, because there's, in the Ice Age cycles and that, and in the Milankovitch cycles, there's 23,000, 41,000, and 100,000 years. There's also a 405,000 year cycle, and that one has existed for so long, they've actually now used it to calibrate the entire geological ages back for tens of millions of years, and it's a figure that's slightly lower than that, but it looks like that might be measuring the same thing perhaps. This is a picture put out by NASA. It's a map of one pole of Jupiter, Jupiter projected onto one pole. Now, I don't know if you can see them. Can you see here a little grey bit here every so often? They're very clear if you get up close. So I went around and counted them in the 72. Now 72 is one of the strong harmonics. 144 and 288 are slightly stronger. And there's a little patch here where they've got every second one, which would make 144. But there are 72 extremely regular formations around one band of Jupiter. Some of these white dots here, they fit more or less to a 24. They do move a little bit, so you see that one's a little short, that one's a little bigger. But doing a 24 around, it does pick up that one, that one, that one, that one, that one, that one, that one. And that one, they're all matching to 24. So we are seeing these strong harmonics 12, 24, 72 appearing. The harmonics theory should work in a closed system. Now, the surface of a planet is not a closed system, but in many ways it behaves a lot like one with the process going on, so we'd expect to see that. We also see, of course, the hexagonal structure on Saturn, which is also a good harmonic.
Sorry, you said harmonics, closed system? What was
harmonics of the circumference, yeah.
Oh, okay.
Yeah, and now this is Christchurch in New Zealand, and there's some little puffs of cloud here, if you can see them, and they're not perfectly regular, but they're fairly regular, and I put next to them the prediction of the harmonics theory for the 34560 harmonic, which is a very strong one, one of the very strongest, and that dividing the Earth's circumference by that, you get 1.16 kilometres, and I put one of these little things next to each one, and you can see that the puffs do like to be that far apart. Now, this is only an indicative thing, it's not proof of anything, but I see these beautiful cloud formations in the sky, but I don't know how high the things are. I can take a photo, but I don't know how high they are. And so it needs space photos, and this is a project I'd really love to see someone do, because other people than me should do tests on this, and this is something somebody could do, to go and get a lot of space photos, find places where there are relatively regular structures, measure the spacing of them in pixels on the picture, determine the scale by looking on a map and getting that, and calculating it out and getting an answer, and doing this many times with many different photos, and then make a histogram of the ones and see whether we get peaks at the place that harmonic theory said they should be. So this is something that other people could do, that all the data exists out there, it's just some analysis that would test the theory further. I showed you the graph of the whole complicated spectrum that I had on 3 lines out to 10 to the 50th. This is the part based on the 1.4 something or other times 10 to 23 years universal cycle. This is the part from the range 200 years down to 30 something years, and then carrying on down to about 3.3 years old. And this is just the spectrum that comes out of that. I've done nothing with it but the standard calculation I showed you of hitting the numbers up and feeding them back in again. And then I put in red here, I've shown the common cycles that Dewey had in red. So those are all common cycles with Dewey that he mentioned, but a number of these other ones are common cycles, like the 59-year one and the 178-year one. So a number of those other ones are commonly reported by people, particularly the pilot guys get of those. So virtually all of the commonly reported cycles are these big peaks that are in here. There's a lot more structure below there. I've only shown that this range is from 0.8 up to 1.1. So it's just showing the very biggest peaks. And then I put in 2 other ones that didn't fit Dewey's ratios of 2 and 3. One of them was the 9.6 year cycle. Now he calls that a 9.6 year cycle, but when he lists those cycles, he lists about half of them as 9.6 years and half as 9 2/3 years. So we can say 9.63 years is about the average of all the ones he's got. The predicted from the harmonic theory is 9.638 years. So it very much agrees. I plotted each of these triangles at exactly the position of the data that I've got information about, and you can see they do hit exactly on these things. It's not as though there's a lot of peaks, you've got to hit something. They are exactly on these figures. And the other one was Dewey's 3.39 year cycle in the share market. That's that one there. Those are not on the ratios 2 and 3, that's on the ratio 7, and that's on the ratio 13 different to the others. This graph now continues onto this part. It's all on one page in my paper, but I put it up here. And the red ones are a continuation of Dewey's common cycles. You can see it's really hitting the biggest ones all along here. 2 years and 3 years are very common, just under those are very common ones as well. And then these blue ones here are the ones that, there's one more red one there. These blue ones there, which are hitting again the very biggest peaks, are the ones that the astronomers have reported in the sun, a whole host of ones there, they're all hitting there. And there are other cycles and other things that do match these other peaks here. I've just put a few of those ones in there to show you that all those cycles those people reported are predicted by the harmonic theory to be very, very strong cycles if we assume the universal cycle is 1.4 times 10 to the 23 years. And incidentally, I fed these known cycles in when I did the analysis to work out how it fits to calculate what is the universal cycle, but I did not feed in that 9.6 year one. It came out as saying there should be one there when you feed it out of it. And it's not obvious at all. Dewey never worked out the relationship of that to the others. So for me that's a test that you're getting out of it things that you didn't put in, and it's agreeing with things that you already know. I mentioned before that the inner planets don't quite fit a wave. If we put a standing wave there from the sun, Mercury's a little bit too far, Earth's a bit close, Mars is missing by a lot. However, the scale of them is at that, and there are a lot of different periods present in the sun that could explain why you get this wobbly nature, that the 5-minute periods, there's a lot of them. But the 160-minute period is just one, and we can see that Saturn, Uranus, Neptune, Pluto all fit. They're all put, that's probably correctly scaled. Neptune's a teeny bit too far, Uranus a teeny bit less, but they're all fitting very accurately to a 160 light-minute wave, and Jupiter on a half of that.
That's
So
a distance from the sun?
these are distances of the planets from the Sun. I've done them as two sets because the other ones are so much closer compared to that. I've shown the ratios there that we got in the graph, about 160 minutes, 80 minutes, and then the series which gives the 6 and 3 minute waves. So I'll talk a lot about 3 and 6 minute waves for the inner planets, 80 and 160 minute ones for the outer planets. And there's a huge, Kotov found everything he analysed, like he did binary stars, he did rotation periods of asteroids and all sorts, and 160 minutes he gets in all of these things. Black holes, it's a common black hole radius is 160 light minutes, and they are finding oscillations coming from those cores of galaxies that are 160 minute oscillations, the Russians. So he's very strong on 160 minutes, and when we look at things like the rotation periods of the planets, Mars and Earth both rotate in about 9 times 60 minutes. Jupiter and Saturn both rotate in about 4 times 160 minutes. And we find this pattern, 4 and 9 are both squares, so we've got n squared times the number. And these formulas that give, and you get another series, the other planets, Pluto is 6.4 days, and Mercury and Venus, and the Sun is 4 times 6.4 days, and Mercury and Venus are other multiples, which are all squares, n squared times 6.4 days. And so those ones, so there are 3 sets of those that all follow n squared, which is very typical of atomic spectroscopy. You have these n squared terms times a number. So the rotation periods of planets are not random, they're all related to these things too. This here is, I got data from this website, which doesn't seem to exist anymore, but they're probably somewhere else, on all the black holes that have measured masses. And this is the mass here, running from 10 to the 6 times the Sun to more than 10 to the 9 times the Sun. And I just put one blob there for each black hole that's been measured. And then I put above here, using the standard relativistic formula for relating what would be the Schwarzschild radius to the mass, how many minutes they are. And you can see there's a huge cluster here around 80 minutes. Another cluster at 160 minutes, my friends there, 240 minutes, 320 minutes, and 480 minutes are present. And again, clusters at 12 minutes and 6 minutes and 3 minutes. So that we can say that those waves that we're getting present here in the solar system didn't originate in the Sun. The Sun is responding. It's a universal phenomenon. It's oscillations of the galaxies, the galactic cores, and it's those waves are throughout the universe. I mentioned before, if we expect space to be periodic with these waves and time to be periodic, then perhaps velocity should be as well. And an explanation of this would be, if you've got an atom and it's got a nucleus, the nucleus has got a lot of mass, and the atom's got the electron sort of repulsion at the outside, if you like. The things that stop us falling through the floor of the man set is that outer part. It's nothing to do with the nucleus. But we've got the inertia of the nucleus. When 2 atoms bang together, the inertia of the 2 nuclei are pushing together, and they are much more massive than the atom wave. And in my view, these successive waves should be at these approximately 10 to the 4.5 power difference. And on that basis, we divide the speed of light repeatedly by about 10 to the 4.5. So we start off with 3 by 10 to the 5 kilometres per second, which is the speed of light. And as we divide, we get 10 kilometres per second, 30 centimetres per second, 10 to the minus 3 centimetres per second, and 3 by 10 to the minus 8 centimetres per second. Now what is that? 10 kilometres per second is the typical speed of the planets and the speed of the stars. It's also the typical speed of sound in solid materials. And when we analyse, we do find a harmonic structure present in the speeds of sound in different materials. We do find a harmonic structure in the speed of light in different materials. The speed of light at 18 degrees centigrade, am I running out of time?
5 minutes.
5 minutes, okay. Then we get that. Then we find that the speed of light in water, the refractive index is given as 1.3333 at 18 degrees C. So the speed of light is 0.75. It's 3 over 4. It's a typical one of the strong harmonic. This one here, the speed of air currents and the speed of heat. We don't usually talk about the speed of heat, but it's a wave equation. It has a speed. This one, 10 to the minus 3 centimetres per second, is the typical speed of ocean currents, and this one translates to 1 centimetre per year, which is the typical speed of continental drift. For those that like stuff that the ancients talked about, earth, water, air, fire, ether. There will be other speeds in between there, it's just these are the more dominant ones because they're the peaks in that graph. This one is one I did, it's unfortunately it's come out small, we won't worry too much. I posted that, this is done about 1994. I predicted I analysed the masses of the different subatomic particles. And I did again using that Kotoff's method, and it gave me two answers for that function I'd like to be a fractions or multiples of. One was 34.76 MeV, and one was double that. And I chose this one because when you had the double one, the proton came out to 13.5. And I wanted it to be a multiple, so I picked this one, and it's now 27. I don't know if you can see here, but going from there, we get reduced by a ratio of 17 to 2 to get to an electron. We go times 3 to get a muon, times 3 gives us proton and neutron. We go times 2 to get us, I can't even read what that one is there, it'll be in my paper here. But you can see all the particles, and there's lots of ratios of 2 there. We have the 17 ratio, and further down here comes a ratio 19 before a whole other bunch of particles, and there's lots more ratios of 2 between the different particles. So this is interesting that we get the 17 and the 19, and then there's actually a ratio of 23 before you get to the Z particles. So we're actually seeing those primes appearing in the correct order as we go to higher frequencies. So that's a confirmation there. And on the basis of this, I predicted there should be such a particle as this in 1994. I got really lucky because only about within 6 months of me predicting it at a cycles conference and on the internet, there was an article appeared in New Scientist saying they're about to publish this article in one of the peer-reviewed journals saying they've discovered this particle and no one was expecting it. Someone was. That's just the table showing the ratios of 2 and 3. We'll leave it out. You've got the gist of that and it'll all be in the paper. Okay, summary and further thoughts. Now there is one more thing after this which I'll do first. No, there isn't. Yes, that's the one I've done it. Okay, so I'm going to read these ones out because otherwise I won't remember them all. Harmonic theory predicts this scale ratios at about 10 to the 4.5. It's the only theory I know of that says there should be these structures present at these ratios in the universe, and there quite clearly are. No other theory addresses that. And to the extent that there are theories that will give a couple of the ratios at the atomic level, they are all done by back engineering those ratios. The numbers, they've got numbers that they don't know where they come from, the fine structure constant and so on. 2 times the fine structure constant squared, which often appears in equations, is moderately close to this number. The fact that we can observe the universe means that there must be non-linear laws to the universe, otherwise we will observe them. If you have non-linear laws in a wave medium, it must develop harmonics for standing waves. It's absolute certainty. The fact that it must, when we look at the structure, it explains all the things. It predicts the scale at which, from the Hubble constant, it gives us the scale. It gives us 0.5 angstroms, which is the hydrogen atom, and 1.3 femtometers, which is the wavelength of protons and neutrons. It predicts that structure that no other theory can do. The idea that matter is, I'm going to give some connections to some of the other ideas that other people developed, many of which have been done at this conference. The idea of matter is nothing but waves. It's called the wave structure of matter, or WSM. This is expressed well in the books of Milo Wolf. There are groups for discussion of these ideas, and I recommend the websites listed on the CRI cycles page. I've put some links for you at the bottom there. The large number hypothesis, known as LNH, may be understood as at a distance of 10 to the 40 of a particle's radius or wavelength, its surface area will be 10 to the 80 times greater. So its outgoing wave will entirely become the ingoing wave of other particles. So that's why what the Hubble scale means is the distance at which the wave from particles, the outgoing, I see a particle as a standing wave. So it's got waves coming in and waves going out, which make standing wave, which are doing this sort of thing as you go out. That's the distance at which the outgoing wave is finally hitting all the other particles and become incoming waves. So you can't detect significantly beyond that. You cannot detect additional matter because its wave can't reach us. These 10 to the 40 number again comes from this 10 to the 4.5. When you get the cube of it, which you get in 3 dimensions, that gives you 10 to the 13.5, which I think you've suggested has something to do with the weak force at some stage. And then you get, and then when you cube that, you get 10 to the 40.5, which is the gravitational relationship. So these are, you can see all these things coming out of these numbers. Lasarde's gravity is to be understood as a sensible explanation. We need to understand that it is based on waves, not particles, and that the outgoing wave really is 1 part in 10 to the 40 weaker than the incoming wave. So energy is being absorbed. The gradual change caused by absorption of energy to the smaller scales, so that this harmonic process continues. The waves that are neutrons and protons are making subharmonics, are making harmonics of themselves, and energy is leaving the smaller scale. And eventually, in the very, very far distant future, much longer than the time scales astronomers talk about, you will get quarks as separate particles that can come loose. So these, it may be the case that in some places such as galactic black holes, the process is already further advanced and they can exist free, and that's why we get such high energy cosmic waves coming from those places. These frequency changes explain not only the fact that gravity really does suck, it really is absorbing, but that particle mass does increase with time, because this absorption means that there's more in the inner wave by the substructure. So the increase in mass with time, I invented this idea and then I discovered I wasn't the first. It's called Narliker's variable mass hypothesis. And what it means is, as the increase with time happens, it means that the frequencies of all frequencies in the spectrum are getting blue shifted because the mass is increased. They all depend on the mass of the nucleus, which is increasing. So those are all increasing with time. Now, if some matter over the far-flung parts of the universe there is at the same frequency as me at some point in time, and then we all increase frequency over some time, the light that's left you earlier when it was a lower frequency, when it reaches me and I'm now a higher frequency, I look at it and I say it's red shifted. It's not, I got blue shifted, and so did you, but I haven't seen that yet. So what's happening is there is no red shift with distance, there is a blue shift with time. That's Narliker's hypothesis, and I arrive at that as a necessary thing that must follow from the harmonics theory. Art was right that central, more massive galaxies are slightly bluer than other galaxies because the same process happens, that they're happening first. I think that's it, and I've put some links on there that may be useful to you, follow some of those things up. And if you want to find my 2 papers, I've stored them on, if you search for Cycles Research Institute, NPA, you will find them.
Thank you very much.
I think we have time for 1, maybe 2 questions.
Yeah.
In the presentation I did, I said that the quantization of gravity produced Bode's law, which seems to be a slightly better fit to the periods of the planets and their cycles, as you would call them, harmonics, than what you have done. But there must be some relationship between the quantization laws and the harmonics. Have you thought about that?
Yeah, well, the harmonics are giving you, like, the outer planets do fit very well as a distance phenomenon, harmonically, but they don't fit well in terms of periods, except for Neptune and Pluto, which are in the 2 to 3. The inner planets fit better on a velocity one. But that doesn't give you either. They don't fit particularly well on period or distance. They fit well on velocity.
I showed that the periods of the planets and the sun lie on a straight line.
Yeah.
And that's also true of the periods of the moons, about the period of a planet on its rotation, on its axis. And so, but there should be a way to take those periods and convert that to harmonics.
Yeah.
And so I'm thinking, and then in the atom you have the same thing.
Yes.
And then in the solar system for the redshifts, Tiff showed that same quantization that produces Bode's law was very accurate.
Yeah.
And so
I'm glad you mentioned the atom, because I took what's called the second spectrum of hydrogen, which are a whole lot of wavelengths that are detected, and I put them in COTOP method, and they gave me a value that everything, and you could see there were musical relationships in it, and the figure it gave me is the most underlying wavelength that they all fitted to. It was, when I divided it by the Bohr hydrogen radius, it gave me 34560, which is my strong harmonic. So it's actually showing that there is that relationship that's happening at the atomic scale.
Right. So the work I did, everything's electromagnetic, so you expect a common set of harmonics on all sides.
Yes. Well, I agree. I have two ways of looking at it. One is it's electromagnetic, and the other way is that it's an ether. I think a tensile ether. But I'm starting to think again after Reg's talk, maybe there's some of this fluid ether, but I don't know. Now, tensile ether I think works, and you can translate that into electrodynamics by the fact that local acceleration becomes the electric force and local rotation becomes the magnetic field and so on. There are two ways of looking at the same thing, but electromagnetism, I think, in terms of the theories, is the most fundamental. If you're looking for the thing as the bottom of the ball, I would say I did that triangular diagram which has got relativity there, quantum mechanics there, and harmonics theory here. I think at the bottom of it all, you get to a wave equations which Maxwell's equations are quite near to. Yeah. So I agree totally with you about it. I'd come to the same conclusion.
One more question. Okay. Oh,
yeah.
Of course.
I was wondering if you by any chance have explored numerology to see if there's similar number patterns.
Yeah, I've had a lot of people call my stuff numerology, and I say no, it's not numerology. Numerology consists of like adding the digits of numbers together, and people like the fact that 3, 4, 5, 6 has got 3, 4, 5, 6 in it. It's irrelevant. If you do it at a different base, it's a different thing. So no, I don't give any importance to numerology.
No. Okay.
Yeah.
I guess.
But they say what you do is numerology.
People accuse me of it, yeah. It's not, it's physics.
Numerology is not an insult.
Yeah, I didn't think it was an insult.
Suggestions been made.